4.7, transformations of a quadratic graph. We're going to write a quadratic function in the form of y equals a times x minus h squared plus k, and we're going to transform the graphs of quadratic functions of the same form. And we're going to do this by using the form vertex form, which is a vocabulary. So we're going to learn what that means. So let's start with standard form. What is standard form of a quadratic equation? So we say standard form, it's simply ax squared plus bx plus c equals 0. Vertex form, it's just kind of like an equation, a formula of just like standard form and slope-intercept form, which is y equals mx plus b. It says y equals a times x minus h squared plus k. Pause this if you need to, but you're going to be writing a lot of stuff, and we're going to write what all these pieces mean as well. But you need to have this in your notes. So what does a equal? A tells us the dilation, meaning a vertical dilation. Is it stretched or is it compressed? It also tells us, does it open up or does it open down based on its sign? X equal h tells us, gives us the axis of symmetry. Okay. H also tells us the horizontal shifts, left or right. K tells us the vertical shift, up or down. It also tells us the value of the minimum or the maximum. Remember, if A is positive, we have a minimum because it opens up. If A is negative, it opens down and we have a maximum. Okay. What else do we need to know from this? Well, we know HK, H comma K, is our vertex. Alrighty. If the absolute value of A is greater than 1, that tells us it's a stretch vertically. If the absolute value of A is less than 1 but greater than 0, then we have a compression. Right? So let's practice writing going from standard form to vertex form. And we're going to do this by using the process of completing the squares. Except it's going to look a little bit different. So look at example 1, page 275. It says y equals x squared plus 6x minus 5. We learned that a has to be positive 1 before we can complete the square. Instead of moving our constant term to the other side of the equation, we're going to leave it here. We're just going to move it down a little bit. And we're going to group this together. And we can do that. We haven't changed anything. So now we take b, 6 over 2 square is 9. So we're going to plus 9. However, when we complete the square, we know that if what we do to one side, we must do to the other side. But we don't want it on the left side. We want y. We don't want it equal to 0. So how do I make this not change? Well, this is really plus 9. If I minus 9, I get a value of 0, and I've added nothing and done no changes. So since I add 9, I'm also going to subtract 9 to the same side. Now I can factor this to x plus 3 square minus 5 minus 9 equals minus 14. Now it's in vertex form. Now I can graph it and write all that information, get all that information by looking at it, the equation. Let's try another one. Let's look at b, because b does not have it in a equal positive 1. It actually has y equals negative 2x squared plus 8x minus 3. So a is not positive 1. So I need to factor out a negative 2. So basically, I'm doing dividing by -2 by factoring out. So this becomes x squared, positive divided by negative is a negative, 4x. Alrighty, so now it's all tied together because I factored it out. So now I take -4, that's our b, divided by 2 and square it, and I get 4. So we're adding 4. Whoopsie, hold on a second. Let's think about this. If I distribute this 2 back to this, I get -2 times +4, which results in -8. So I've really subtracted 8 from this whole piece right here. So what's the opposite of -8? Because I need to make it 0 so I don't change the equation. I need a +8. So now I can factor this. 8x minus 2 squared minus 3 plus 8 is +5. Now it's in vertex form. Let's look at example 2 on page 276. They say write which is an equation shown of the function below of the graph. Okay, I'm not going to make this really pretty. We can write an equation if we know the vertex and any other point on the graph. So they give us the vertex, 3, 2, and they give us this coordinate, -1, -2. So we said we need a vertex, right? H, K, and we have 3, 2. We need a point, some x, y. We have -1, -2. Let's start with our equation in vertex form. X minus h squared plus k. So let's take this. We don't know what a is. Oops, actually. Do we know what y is? Yeah, we have a point. It's -2. I don't know what a is. I know what x is. It's -1 minus, what is h? 3 plus k is 2, and this is squared. So -2 equals a times -4 squared plus 2. -2 equals a times 16 plus 2. I'm going to minus 2 from both sides, and I get -4 equals 16a. Divide by 16, divide by 16. A equals -1/4. So all I need is a and my hk to write my equation. So y equals -1/4 x minus 3 squared plus h. So we see it does open down. Oops, it's 2, not h, it's k plus k. So now that's my equation, which was b. All right, let's look at the transformations of the quadratic function. So we said h tells us you move right or left by that many units. So if it's positive, you move to the right. If it was negative, you would move to the left. If k is positive, you move up that many units. If it's negative, you move down. If a is negative, it's going to reflect over the x-axis. If it's positive, it's just going to open up. If the absolute value of a is greater than 1, it's going to have a stretch. It means it's going to get thinner. If the absolute value of a is less than 1 but greater than 0, we're going to have a compression, and that is actually going to get fatter than the original parent function. All right? So I need you to do problem number 2 on page 278 and take good notes.